Good evening. I, Surinder Singh Chabra, student of BTech CSE, first year, first semester of VIT University, Vellore, would like to put forward my viewpoint on the topic nanotechnology. As an essential, the evaluation component of FAT Lab Assessment 3 in English 1902, Technical English 2. Discussion on the topic chosen nanotechnology within the stipulated time of 10 minutes only. Nanotechnology is so called the next big thing, but it is not wrong. As if we imagine a normal laptop, PC, same as size of a wristwatch. Interesting, right? For basics, nanotechnology is study of controlling an atom at a molecular level. Average size of a nanomaterial is about the size of a human hair, that is 80,000 nanomaterial. At that size, all laws of study of physics and chemistry fail, and it follows a different theory and a different world which we call the quantum world. According to scientists, the quantum world is the world that's smaller than an atom. Things at this scale don't behave the same as we see on a normal scale. According to study, to enter quantum world, we need to be a size of a nanomaterial. Time moves slowly in quantum world, and some scientists believe it is a pathway to travel between time. The ideas and concepts behind nanoscience and nanotechnology started with a talk entitled There's a Plenty of Room at the Bottom by physicist Richard Feynman at American Physical Society meeting at California Institute of Technology on December 29, 1959, long before the term nanotechnology was used. Over a decade later, in the exploration of ultra precision machining, Professor Nario Tanguchi coined the term nanotechnology. It wasn't until 1981 that the development of scanning tunneling microscope that we could see an individual atoms that nanotechnology began. Sorry. Nanotechnology can change the world in the way we never ever imagined. As always, it is also called a Swiss knife that has two parts, including losses and as well as benefits. Scientists currently debate the future implications of nanotechnology. Nanotechnology may be able to create many new materials and devices with a vast range of applications such as nanomedicine, nanoelectronics, biomaterials, and consumer products. On the other hand, nanotechnology raises many of the same issues as new technology, including concerns about the toxicity, environmental impact, and their potential effects on global economies, as well as speculation about various doomsday scenarios. The concerns have led to a debate among advocacy groups and governments on whether special regulation of nanotechnology is warranted. In nanotechnology, two types of approaches are followed. First one is bottom-up approach. They seek to arrange smaller components into more complex assemblies. DNA nanotechnology utilizes the specificity of Watson-Crick base pairing to construct well-defined structures out of DNA and other nucleic acids. Approaches from field of classical chemical synthesis, inorganic and organic synthesis also aim at designing molecules with well-defined shape. Example, bispeptides. Top-down approach. These seek to create smaller devices by using large ones to direct their assembly. Many technologies that descended from conventional solid-state silicon methods for fabricating microprocessors are now capable of creating smaller features smaller than 100 nanometer, falling under the definition of nanotechnology. Giant magneto-resistant based hard drives are already on the market that fit this description, as do atomic layer deposition techniques. Peter Grunberg and Albert Fade received the Nobel Prize in Physics in 2007 for the discovery of giant magneto-resistance and contribution to the field of spintronics. Nanofibers are used in several areas and in different products, in everything from aircraft wings to tennis rackets, and here we can see they are also used in carbon nanotubes, scanning tunneling microscope, as well as nanorods. Nanofibers are also used in several areas, in different products, in everything from aircraft to a tennis racket. Inhaling airborne nanoparticles and nanofiber may lead to a number of pulmonary diseases, example fibrosis. Researchers have found that when the rats breathed in nanoparticles, the particles settled in the brain and lungs, which led to a significant increase in biomarkers for inflammation and stress response, and that nanomaterials induce skin aging through oxidative stress in hairless mice. A 2-year study at UCLA's School of Public Health found lab mice consuming nanotitanium oxide showed DNA and chromosomes damaged to a degree linked to all the big killers of man, namely cancer, heart diseases, neurological diseases, and aging. For the future, there's a lot of scope in nanotechnology. It is very interesting. See our superheroes converting a small wristwatch into a weapon. If we consider future, wearable fitness technologies means we can monitor health by strapping gadgets to ourselves. There are even prototype tattoos that can sense our vital signs. But by scaling down this technology, we could go further by implanting or injecting tiny sensors inside our bodies. This would capture much more detailed information with less hassle to the patient, enabling doctors to personalize their treatments. These sensors usually rely on nanomaterials and manufacturing techniques to make them smaller, more complex, and more energy efficient. For example, sensors with very fine features can now be printed in large technologies on flexible rolls of plastic at low cost. This opens up the possibility of placing sensors at lots of points of critical infrastructure to constantly check everything is running correctly in bridges, aircrafts, and even nuclear power plants, which are mainly based on the molecular levels and can create destruction. If cracks do appear, then nanotechnology play a further role, changing the structures of materials at nanoscale and can give them some amazing properties by giving them a texture that repels water. For example, in the future, nanotechnology coatings or additives will even have the potential to allow materials to heal when damaged or worn. For example, dispersing nanoparticles throughout a material means they can migrate to fill in any cracks that appear. This could produce self-healing materials for various from aircraft cockpits to microelectronics, preventing small fractures from turning into large, more problematic cracks. In the future, nanotechnology could enable objects to harvest energy from environment, which would create less dispersion of energy and more usage. New nanomaterials and concepts are currently being developed that show potential from producing energy from movement, light, variations in temperature, glucose, and other sources with high efficient conversion. Because of the variety of applications, including industrial and military, many governments and countries had invested billions of dollars in nanotechnology. Prior to 2012, the USA invested 3.7 billion using its National Nanotechnology Initiative. The European Union invested 1.2 billion and Japan alone invested 750 million. Over 60 countries created nanotechnology research and development (R&D) departments between 2001 and 2004. In 2012, US and EU each invested 2.1 billion on nanotechnology, followed by Japan, which is 1.2 billion. Global investment reached 7.9 billion in 2012. Government funding was exceeded by corporate R&D spending on nanotechnology research, which was 10 billion in 2012. So as we see, many governments are investing more and more in nanotechnology, but it has some effects and some benefits also that future will only tell. Thank you for my time.